You would not die instantly. That's the part nobody tells you. Falling into a black hole isn't like hitting a wall. It's slower, stranger, and somehow worse. Because your body would start to notice something is wrong long before anything actually kills you. Here's what really happens, second by second, if you fell into one. Let's say you're in a spaceship and you're falling toward a black hole about the size of the one at the center of our galaxy, Sagittarius A star, 4 million times the mass of our sun. From far away, nothing seems unusual. You're just falling, weightless, same as floating in orbit. But there's an invisible line out here called the event horizon. Cross it, and you can never come back. Not because of some force field, but because space itself is falling inward faster than light can escape it. Light, the fastest thing in the universe, can't get out. And here's the first strange part. You wouldn't feel yourself cross it. No bump, no flash, no warning sign floating in space that says, "Last exit." You'd check your instruments and see nothing unusual. You just crossed the point where the universe stopped letting you leave. Meanwhile, someone watching you from a safe distance would see something completely different. To your friend back on a space station, you wouldn't just vanish. You'd appear to slow down. Slower? Slower still? Your image would freeze at the edge of the event horizon, getting dimmer and redder, stretched out over, theoretically, forever. This is time dilation. Gravity. This strong doesn't just pull on matter, it pulls on time itself. From the outside, you're frozen at the edge, fading like a photo left in the sun. From the inside, you already crossed. You're gone, falling. Two completely different realities, both true at once. That's not science fiction. That's Einstein's general relativity, confirmed by observation. But things are about to get physically unpleasant for you. Yes, that's the real scientific term, spaghettification. As you fall feet first, gravity pulls harder on your feet than on your head because your feet are just slightly closer to the black hole. Not a big difference normally, but near a black hole, that difference becomes extreme. Your body starts to stretch. Your feet accelerate away from your head. Eventually, the pull is strong enough to separate atoms from atoms. Now, here's a twist. Most videos skip. The size of the black hole changes everything. Fall into a small black hole, a few times the mass of our sun, and spaghettification happens before you even reach the event horizon. You're torn apart in open space. Fall into a supermassive black hole, like Sagittarius A star, and the gravity gradient is gentler. You could cross the event horizon completely intact. Alive? Confused, but intact. That's once you're inside the event horizon, something bizarre happens to your sense of direction. Toward the black hole stops being a direction in space. It becomes a direction in time, like toward tomorrow. You can't avoid it the same way you can't avoid getting older. Every possible path, every direction you could steer your ship leads to the center. There is no away anymore. Looking up, you might see the entire history of the outside universe compressed and warped above you. Light from stars, maybe even light from your friend back on the station, still trying to reach you, arriving all at once in a final distorted burst. Then, in a fraction of a second that might stretch subjectively longer depending on the black hole's size, you reach the singularity, the center, where our current laws of physics simply stop making predictions. Not, we don't know yet. Stop. General relativity itself breaks down at that point. Nobody knows what happens there. Not theoretically, not hypothetically. It's the edge of physics itself. Here's the detail that keeps physicists up at night, and it's called the information paradox. Everything that falls into a black hole, every atom of you, every memory encoded in the arrangement of your neurons, should, according to quantum mechanics, never truly be destroyed. Information isn't supposed to just disappear from the universe, but black holes eventually evaporate over unimaginable timescales through a process called Hawking radiation. And when they do, where did you go? Where did the information go? We don't fully know. It's one of the biggest unsolved problems in modern physics, and it's the collision point between two of our best theories, general relativity and quantum mechanics, that currently refuse to agree with each other. So would you die instantly? No. Would you feel yourself cross the point of no return? No. Would the universe even agree on what happened to you? Also no. If you want the next one, what's actually on the other side of a black hole, like and subscribe.